Okay, good morning, everyone. Yeah. So we are going to study, continue our study of row reduction. So the big topic is row reduction. So the idea is that you start with a m cross n matrix. It's an algorithm whose input is a m cross n matrix. A, and just 1 second. I have to be sure that my indices are correct. Yeah. And the output is a m cross n matrix A prime in row echelon form. So I have to define what I mean by row echelon form. I don't know if I will get to that today. Hello, did somebody say anything? Okay. So a matrix in row echelon form has a very specific shape, and the row reduction algorithm takes you from an arbitrary m cross n matrix to matrix A prime in row echelon form, and so the matrix A prime associated to A is actually unique. And how does the algorithm work? Algorithm proceeds by finding the sequence. So it's a finite sequence. It's not. It's a finite sequence, but the number of elements will depend on the input matrix of elementary matrices of size m cross m. So if the input is a matrix of size m cross n, you should look at the first index m, and the elementary matrices that you look for will be of the size, will be square matrices of size m cross m, where m is the number of rows of the input matrix. So m equals number of rows of the input matrix A. So now elementary matrices, these are square matrices of a special kind, and well, there are three different types of elementary matrices, which we've already seen in the last lecture. So much of today will be spent describing what elementary matrices do. So today we will do two things. One, revise the description of the three types of elementary matrices. And describe in words and equations what an elementary matrix does to do two different kinds of objects. So what an elementary matrix does. So that is again an English phrase which I have to make precise. So the point is, what can you do with a M cross? So let me take an elementary. So I have yet to revise the three different kinds of elementary matrices, but I'm sticking with point 2 now. I want to tell you a bit more what I mean by what an elementary matrix does. So what does this mean? So what does this mean? By this I mean so it means two things. So that I'll explain both things. In fact, okay. So take an elementary matrix A, E. Okay, this is a M cross M matrix. Now I'm going to multiply it on the right by another matrix. Okay, so a second matrix, and I will describe the result. Okay, so that is what this phrase means. What does an elementary matrix do? Okay, now if I have an M cross M matrix E, and I'm multiplying it with another matrix on the right. The matrix, I have not given it a name, but it is within the square bracket. What should be the size of this? So I want you guys to tell me what are the possible sizes of a matrix that I can multiply on the right.
So the result is the M cross N matrix?
No, the result is the size of the result will depend on what matrix I put in the square bracket. But what are all possible sizes of matrices I can put on the right of E?
So M cross something.
Yeah, yeah. So the size has to be, the number of rows of this matrix must be the same as the number of columns of E, but the number of columns of E is M. So this will be M cross something. So let me say N. For N can be anything. Okay. So I'm going to describe what it does, what happens when I take an arbitrary M cross N matrix. Let me call this B. And so this I'll call B prime. So now, but before I go back to go further with elementary matrices, let me finish this sentence. So the algorithm proceeds by finding a finite sequence of elementary matrices E1. Let me again keep the same sequence as in the notes. Yeah. E1, E2, Ek, and the output A prime is got by taking Ek minus 1, E1 times A. Okay, so the algorithm, to execute the algorithm, what you will do is find a finite number of elementary matrices E1 to Ek, take the matrix A, multiply on the left by E1, then multiply that on the left by E2 and go on until, and then finally finish by multiplying by the kth matrix. Now K will depend on A. For example, if A is already in row echelon form, then you don't have to do anything. Okay, so you still don't know what row echelon form is. I have not explained to you that. But to explain, but to get to the algorithm and everything, we need to first understand elementary matrices and what they do. Okay. Now, so let me go back to the description. Yeah. So now, what is the simplest value of n that I can take?
1.
1. So I'm going to now describe the 3 types of elementary matrices, and then in each case, tell you what happens when I multiply M cross 1 matrix with E on the left. There is another name for M cross and 1 matrix. What is that? Hello?
I'm a column vector, sir.
Column vector. So what are we going to do? We are going to now describe again, because we already in the last lecture, we did this somewhat quickly. Describe in each case when you multiply a column vector of length m, length m by an elementary matrix of the corresponding kind. Okay, so this is what I'm going to do. So recall what is the, so let me just very quickly remind you of the 3 types of elementary matrices, the shape, okay, and then we will again slowly go through each type, okay, the 3 types. So the first type is this 1, 1, dot, 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 1. All entry is 0 except some entry here, which is A. Okay. And of course, here in this picture, A appears above the diagonal. So this is the diagonal is this is the diagonal of the matrix. And in this example, A is appearing above the diagonal. You could have A appear below the diagonal also. That is also of this first kind only. So this is the first kind. So let me put that down. A here and everywhere else 0. Okay. So now A, the non-zero entry is below the diagonal. So these are both elementary matrices of the first kind. Of course, if A is 0, this is just the identity matrix. So that is nothing special. So we will assume that A is non-zero. Okay. So of the first kind. Now, the elementary matrix of the second kind. That looks like this. 1, 1, 1. So you start with the identity matrix of size m cross m. But then you pick I and j, I not equal to j. So pick I and j. And then you do the following. You make the 0 here, make the 0 here, make this 1 here, and make 1 here. So this is the elementary matrix of the second kind. And the third one is this one. So you start with the identity matrix. So let me start with the identity matrix. And then if I look at the ith diagonal entry, you take this 1 and change it to some C non-zero. So this is third kind. Okay, so is there any question about, do you understand that the definitions of the three kinds of elementary matrices? Is there any, does anybody have a problem with this?
Sir, in the third type.
Well, just 1 second, let me just, yeah.
Sir, in the third type, can C be 1?
Well, so the point is, if C is 1, then it's the identity matrix. So, so in fact, similarly, in the first case, if A is 0, it's again the identity matrix. And so you kind of rule that out because you don't want, okay, so your question is the identity matrix an elementary matrix? Yes. That I'll have to ask my lawyers about this. Okay. So no, this is almost a matter of definition. I have to check. Okay. Yeah. So for today, let us agree that the identity matrix is not an elementary matrix, but it's a point that has to be clarified. I'll clarify it and let you know. Okay.
Sir, what you said right now we're assuming that it's not an elementary matrix, right?
That for the moment, until as I said, until I speak to my lawyers.
Okay, sir.
Yeah. I'm joking. This is it is important to be clear on this, because otherwise the statements that I make may not be strictly correct. I have yeah. So I will deal with this. Okay. For the moment, let's assume that we don't think that the elementary matrix identity matrix is an elementary matrix. Okay. Is it okay?
Yes.
Yeah. So now let us see. Okay. So the first thing is, let me get one small matter out of the way. Some of you might, Amit, did you want to ask something? No. Okay. Yeah, let me get something out of the way. Some of you may be uncomfortable that I'm describing things in terms of pictures and not in terms of equations. So let us first deal with that. Okay. So let us first the three types of elementary matrices. Maybe I won't do it for each kind. I will do it for one kind, and then you will see how to do it for in terms of the basis matrices EIJ. Do you recall the basis matrices EIJ for the space of M cross N matrices? These are matrices, all of whose entries are 0 except the entry at the intersection of the ith row and the jth column, which has value 1. Okay, these are so for example, so if example, so if M equal to 2, there are 4 of them. These are the, this is E11, this is E22, this is E12, and no, I got it wrong. I think this is E12 and this is E21. It could be the other way. I think this is one second. Okay, so if I look at M cross M, there are EIJ, I 0 less than or equal to I less than or equal to M, 1. There are these M squared matrices of size M cross M, which form a basis for this vector space. And you can describe elementary matrices in terms of this basis. For example, the first kind is of the form identity plus A EIJ I not equal to J. Elementary matrix of the second kind is I minus A EII minus EJJ plus EIJ plus EJI I not equal to J. Third kind, I plus C minus 1 EII. Okay, so this is a way of describing elementary matrices of the three kinds in terms of these basic matrices EIJ. I'll wait for the helicopter to pass. And so let me address again, there was a confusion already in the last lecture. Let me address that, because now we are going to act with these elementary matrices on the space of column vectors, and that space has its own basis with only one index, E1 to En. This Eij are square matrices of size M. So that is why there are two indices, Eij. I forget who was asking the question last time. I think, was it Rajagopalan? Somebody had a question about the two indices in the Eij. I hope this is
yes,
clear
sir.
now. Yeah.
Yeah, it's
Yeah,
Swaminath.
Yeah. Are you okay now?
Yeah, I'm fine, sir.
Yeah. Okay. So does everybody understand this description in terms of equations of the three different kinds of elementary matrices? So, for example, do you understand this? I should put an index M here. This is the M cross M identity matrix. IM is the M cross M identity matrix. So do you want me to, does anybody want me to explain this? Nobody. Everybody understands this. Okay, let me ask, how many elementary matrices of the second kind are there? Supposing I fix M, how many elementary matrices of the second kind exist?
So M squared minus M.
Sorry?
M squared minus M.
Are you sure? Are you overcounting?
I think we will have to divide that by 2.
Yeah, it is M choose 2 because, right? Because you choose two indices I and J which are different, and then you get this elementary matrices, but the order is not important. So who said M squared minus M? Was that Siddhant?
Yes, sir.
Yeah, so do you see this, that you have to divide by 2?
Yes.
So it's really M choose 2, yeah? How many types of how many elementary matrices of type 3 are there?
Sir, M.
There are M. And how many types of elementary matrices of type 1 are there?
So this will be and this will be MP2, right? Because here Ij will matter.
Square M, I think.
Yeah, so just think of the shape and then it'll be clear, right?
Sir,
How many places can the A occur in? A can occur in any place in the matrix except on the diagonal.
M squared minus M.
It's M squared minus M. Let's go back here. This A, this A can occur in any non-diagonal spot, and there are M squared minus M non-diagonal spots. So
Siddhant did say MP2, which is the correct answer.
sorry.
Siddhant did say MP2, which is the correct answer.
Okay, so the only trouble is I don't know what MP2 is. I know M choose
Permutation.
Permutation. Okay, very good. Yeah. Very good. So everybody understands the three types of elementary matrices. Now let us deal with what they do to column vectors of size M. So it's easiest to deal with the third kind. So let E1 to EM be the standard basis of M cross 1 column vectors, which is column vectors of length m. So E1 is this column vector, E2 is 0, 1, 0, and EM is this. Okay, so everybody understands this. Okay, so now if I take an elementary matrix of the third kind, IM plus C minus 1 EII, and act on EK. Okay, so Swaminath and Rajagopal, so watch out. There are two different kinds of E's here. This is a M cross M matrix. It's part of a basis of M cross M matrices. This is a column vector, and it's part of a basis for column vectors of length m, and the result is going to be a column vector of size m. And what will it be? So let us you see, this is why equations are terrible. So because this way of writing the thing, it's, you have to really work hard to understand what's happening. But if you just write this out, what does this do? This comes in the this thing I get C here. So this is this matrix. This matrix is this. Does everybody agree with this?
Yes, it's
Does everybody see why I need that C minus 1 here?
Yes, sir.
Yes, sir.
Yeah. Huh? Yeah, why do I need that C minus 1? Because the identity matrix in the diagonal spot, the identity matrix contributes 1, and C minus 1 times the EII contributes C minus 1. Okay, so when I add up, I get C. Chauhan, do you see?
Yes, sir. Yes, sir.
Yeah. Okay, so now if I take my basis column vector EK, which is 0, 0, 0, and at the kth spot I get 1. So this is the kth spot, and 0, 0, 0. What will I get? This will be equal to. So supposing k is not equal to I, what will happen? Well, I will just get back EK. Okay, so this is EK, and this will give me EK if k is not equal to I. But if k is equal to I, if k is equal to I, then this will be, the 1 will be in exactly the same spot, exactly at the same level. So I will get C times EK if k equal to I. Okay, so the elementary matrix of the third kind, what it does is it leaves all the other basis vectors of column unchanged, but the ith basis vector, it multiplies by C. Now, from this description, you can say, what is the inverse of this?
So could we replace C with 1 by C?
Yeah, that is so. So there are two ways of answering this question. So one is just as you did. So I look for a matrix. So I have this matrix 1, 1, 1, C 1, and then supposing I'm looking for a matrix that when I multiply on the left, so gives me 1, 1, 1, 0, and it's clear that what will work is this one in exactly the same spot where C is. I put 1 over C. Okay, so the inverse matrix is 1 over C, but you can also see from the action on basis vectors. So I have one linear map which leaves all the basis vectors unchanged except the ith basis vector that gets multiplied by C. So what should be the inverse map? Well, the inverse map should leave all the basis vectors unchanged except it should multiply the ith basis vector by 1 by C. And what is that matrix? It is exactly the matrix that we wrote down. So the inverse matrix you can get in two ways. One, by inspecting the matrix and seeing what the inverse should be. The other, in terms of what the original matrix does to vectors. And in this case, it's easy because the description of how it acts is very clear. It does nothing to all the basis vectors except one, and that basis vector gets multiplied by a scalar C. So now if you find another linear map which does the inverse multiplication on that basis vector, the composition of the two linear maps will give you the identity. So this is an example of a phenomenon that if you want to understand something about a matrix, it's often useful to have a description in terms of its actual action on a basis. Very good. So we now know what the inverse matrix is, and you note that the inverse matrix is also an elementary matrix. So let me put that in red. Inverse matrix is also an elementary matrix of the same kind. Well, what kind are we now discussing? We are discussing elementary matrices of the third kind. Okay, so the inverse matrix is also an elementary matrix of the third kind. And in fact, I can write it down in terms of the formula that I plus C minus 1 times EII inverse is IM plus 1 over C minus 1 EII. So this is nothing except, so this matrix is exactly this. This is just a fancy way of very good. So now, so for the third kind we have done. So third kind. Okay. Now second kind. So let's do it slowly. So recall that the second kind is this. So this is I. This is ith place. So now supposing I take the column vector ek, which is 1, 1, 1, 0, 1 in the kth place, and 0 everywhere. What does this do?
If k is not equal to I and k is not equal to j, then the same ek.
Yes. And if k equal to I,
Then
it will give EJ. It will
yeah. So
interchange.
let me just write I am plus ij plus eji. Let me just do it in the same way as minus ei minus ejj plus eij plus eji acting on ek. Now tell me, this is equal to ek if k is not equal to I or j, if is equal to ek, ej if k equal to I, ei if k equal to j. Does everybody agree? So what this matrix does is it leaves all the basis vectors alone unless one of them is ei or ej, and if when it hits ei, it spits out ej, and when it hits ej, it spits out ea. It interchanges the two basis vectors, the jth basis vector with the ith basis vector. Okay. So for example, if m equal to 3 and I, j are equal to I equal to 1 and j equal to 2, what does this do? Well, this is 1, 2, 3. So what does this do to a point with coordinates x1, x2, x3? Okay, let me write it like a column vector, x1, x2, x3. Now if I act with this matrix, so let me call this matrix I12. What will this do?
It interchanges first and second entry.
Yeah. It will give you x2, x1, x3.
So can you explain how you label the axes with 1, 2, and 3?
Because
just-
well, I should really speaking label them E1, E2, E3.
Okay, so thank you.
Yeah. Okay. It's better, no? Because I've identified column vectors of length 3 with R3. And so then the usual basis vectors in R3 I have to call E1, E2, E3. That's all. Is that okay?
Yes.
So now from this description, you can ask, I can ask you, what is the inverse? First of all, is it invertible? It is indeed invertible. That is pretty much clear. And or in fact, we will see it simultaneously as answering this question. What is the inverse of this guy?
Itself.
Is itself.
Yeah. So the claim is that the inverse of this this matrix is itself. That is clear because if I act with this corresponding matrix twice, what will it do? All the basis vectors other than EI and EK stay as they are, and EI gets flipped to EJ and then flipped back again to EI because you are operating twice with the matrix. So the answer is itself. So again, it's the elementary matrix of the second kind. Its inverse is in fact itself, so it's an elementary matrix of the same kind. Let me just make sure that everybody is on board. Whom should I ask? Srimati, you're one of the few people who keep your video on. Thanks for that. It's really good to see a face. Are you okay with this?
Yes, sir.
Yeah. Let me just go down and ask Rupunjay. Not there. Naveen Surya. Yeah. Shakti Chauhan, you got disconnected. So let me see. Do I need to? Could you explain this example again? Which one? I12.
Yes, sir.
Yeah. So yeah. So yeah. Thanks for the question. So the question is, so I'm looking at a particular case of M. I'm taking M to be 3 so that we can visualize things. So and then column vectors of length 3, I am identifying with the usual R3. So do you understand that identification, Shakti?
Yes, sir.
Okay. So now so now there are, as we said, to describe a matrix of the second kind, I have to choose two different I's. Okay, I have to choose an I and a J, which are different from each other, and I choose I equal to 1 and J equal to 2, because this is an example. Okay. So if I do that, what will the corresponding matrix look like? So I didn't write it down, but let me write it down. The corresponding matrix, which I call I12. I am giving this matrix a name, but first let me tell you what the matrix looks like. The matrix will look like this: 0, 1, 1, 0, 1, 0, 0, 0, 0. And I give it a name. I just call it I12, just to have some. So do you first of all agree with this?
Yes, sir.
Okay.
Yes, sir.
So now I have to see what it does to this column vector x1, x2, x3, right? And it is clear what it does is x2, x1, x3, because that is how matrix multiplication works. Do you first agree with that? I'm not finished with this. I think I'll say something else that will probably help you. But do you agree with this matrix multiplication?
Yes, sir. Yeah.
Okay, so this is what we said here. I12 acting on the column vector x1, x2, x3 gives you x2, x1, x3. In geometric terms, what it does is take a vector like this and get you a vector like this. So it keeps the third component unchanged, but it changes the 1 and 2 components. So this is what I12 does to a vector in geometric terms. And this vector goes here, which is why when you do it twice, you get the identity linear map. Okay, so now let me just say something that will probably help you. So another way of understanding this equation is I12 acting on x1, x2, x3 is I12 acting on x1 times E1 plus x2 times E2 plus x3 times E3. Right here, this is a scalar. This is a column vector. Do you understand? Do you agree with this, everybody? Shakti, do you agree with this?
Yes, sir.
Okay.
Yeah.
Now I12 is linear. So this is I1 times x1 times I12 acting on E1 plus x2 times I12 acting on E2 plus x3 times I12 acting on E3. But we know what I12 does to E1, it makes it E2. And I12 acting on E2 gives you E1. And I12 acting on E3 gives me E3 back again. So you get this. But now you write even, so what is this? This is x1 times 1, 0, 0 plus x2 times, 0, 1, 0, 1, 0, 0 plus x3 times 0, 0, 1, which is 0, x1, 0 plus x2, 0, 0 plus 0, 0, x3, which is x2, x1, x3. So it is all consistent. Was that helpful?
Yes, sir.
Yeah. Very good. So now I'm not going to deal with the first case, but again, the same thing is true that the inverse of, of a, so if I take an elementary matrix of the first kind, its inverse is also of the first kind. In fact, it's got by taking A and I should, every time, this is an elementary fact, but I get confused each time. So let me just make sure. No, it's also a matrix of the second. I don't want, there is something, the inverse is got by, if I remember right, just flipping the sign on A. Maybe I need to put it in the opposite.
Yes, sir.
also,
I mean,
yeah, is that
negative
correct?
A will work. Yes, sir. Negative A will work.
That is all, no? Yeah.
Yes, sir.
Very good. So now let me take a break and then we will come back. So let me repeat. What we want to understand is what happens when I take a matrix of size m cross n, where n is not necessarily 1, and multiply it by an elementary matrix on the left of size m cross m. So to understand this, you have to understand a basic fact about matrix multiplication, which I am describing in this context. But it's something that I mentioned in the notes, and this is something that you should really, it's a very simple fact. So think of this m cross n matrix, okay? How many columns are there? There are n columns. And how many entries are there in each column? There are m entries. So in fact, you can think of the m cross n matrix as a row, one consisting of only one row, but each of the entries is actually a column vector. So that is all I have done. So I've called the first row of the matrix V1, second row V2, and the nth row Vn. So these are column vectors. Now take any matrix that need not be elementary. So let me just cross out the elementary here. Call that matrix A. Call this matrix B. So B consists of these n column vectors. AB has a very simple description. I take the first column vector V1, multiply by A on the left, take the second column vector V2, multiply by A on the left, and take the nth column vector, multiply by V on the left. So each of these is the column vector. So when you first encounter a matrix multiplication, this is something that you often don't see, but after somebody points this out to you, it is immediate. Okay. So now if A is an elementary matrix, and you want to know what happens when I multiply an arbitrary m cross n matrix by A, because you already know what happens when the elementary matrix acts on column vectors, you can easily read off what happens when the elementary matrix multiplies an arbitrary m cross n matrix. For example, elementary matrix of the second kind, what it does is it exchanges 2 rows of the matrix on the right. Elementary matrix of the third kind does nothing to all the rows except 1, and that row, each entry gets multiplied by the same scalar. And elementary matrix of the first kind, what it does is it adds a scalar multiple of 1 row to another row. Okay, so now with this, I'm going to really stop the recording, and I will stop the class at this point, but this is where we will resume. So let me just repeat. We have 3 different kinds of elementary matrices. These are all invertible matrices. The inverse of an elementary matrix of some kind is an elementary matrix of the second kind. For each kind of elementary matrix, first you can see what it does to column vectors, and then using this remark, which is enclosed in the red box, you can easily see what the elementary matrix does to an arbitrary m cross n matrix when it multiplies it on the left. Let me repeat. In the elementary matrix of the first kind, when it multiplies an arbitrary matrix on the left, what it does is, the result is you take 1 row of the matrix multiplied by a scalar and add it to another row. If it's a second kind, you exchange 2 rows. And if it's a third kind, 1 row gets multiplied by a non-zero scalar. Now, this is what this is explained in the notes. I'll update the notes. You can read them. And we will resume at this point with a little more explanation. And the final result of the section, which we will not prove, is that any m cross n matrix can be brought to row echelon form by multiplying by a suitable sequence of elementary matrices. And since you know what elementary matrices do to matrices, this can be re-expressed by saying that any m cross n matrix can be brought into row echelon form by a sequence of elementary operations. And elementary operations are adding a multiple of a row to another row, exchanging 2 rows, and multiplying a row by a non-zero scalar. So all this is what we will see in the next lecture. Okay, I will stop now.